A 19-mile section of the Earth's crust in Yellowstone National Park has begun to swell. Not an earthquake, not a landslide, but a silent, steady inflation of the ground itself. Since July of 2024, an area of land roughly the size of the city of Chicago has been rising, measured in increments of millimeters, pushed up from below by a force that no one can see. The official name for it is the Norris Uplift Anomaly, but its return after years of quiet dormancy is forcing scientists to look again at a very old and very cold threat to the north, a threat that has nothing to do with wind and everything to do with physics. Curious what you think about this actually? Let me know in the comments below. To understand the shift, you first have to understand that Yellowstone breathes. The entire 34 by 45 mile caldera, the collapsed remnant of a civilization-ending eruption 640,000 years ago, is not static ground. It is the surface of a complex living geothermal system. Using networks of high-precision continuous global positioning system stations, or CGPS, and satellite-based radar, scientists can watch the ground rise and fall like a colossal lung. This breathing is usually concentrated over two main areas inside the caldera boundary, the Mallard Lake Dome and the Sour Creek Dome. Over years, they will inflate by a few inches as magma and superheated hydrothermal fluids move around miles below. Then, just as slowly, they will deflate, an inhale and an exhale on a geological timescale. That is normal. But the recent bulge is not happening at those locations. It is centered at the Norris Geyser Basin, a famously volatile and hot patch of ground that sits just outside the northern rim of the main caldera. This is the Norris Uplift Anomaly, a feature with its own distinct and troubling history. The first time it was documented with modern instruments was between 1996 and 2004, when the ground there swelled by almost 5 inches. Then it stopped. The pressure subsided. Now it is back. Data from the Yellowstone Volcano Observatory, or YVO, tracked the ground at Norris beginning to rise in July 2024. Through the rest of the year, it steadily climbed. By December, the total uplift measured approximately 1.5 centimeters, or just over half an inch. Then, in January 2025, the inflation abruptly stopped. The ground is no longer actively rising, but the bulge remains, a permanent half-inch warp in the crust over a 30-kilometer wide area. Here is the detail that tells the real story. This deformation is not a sign of an imminent eruption. Michael Poland, the geophysicist in charge at the YVO, has been clear that these events are driven by processes deep underground, likely between 6 and 10 miles down. The culprit isn't a massive volume of magma rushing toward the surface, but more likely a small intrusion of new magma into the system, or the pressurization of the vast network of hydrothermal fluids that feed Yellowstone's famous geysers. Jamie Farrell, the chief seismologist of the YVO from the University of Utah seismograph stations, tracks the thousands of tiny earthquakes that accompany this movement. These swarms of low-magnitude tremors are the sound of the rock cracking and shifting as fluids are forced through the subterranean plumbing. It's the volcano clearing its throat, not preparing to scream. But the return of this specific anomaly, this persistent swelling at Norris, serves as a powerful reminder of the energy contained beneath the park. It forces us to ask a different and far larger question. If the system were to truly erupt, where would the danger really lie? The common answer, for decades, has been a comforting one: east and southeast, carried on the prevailing winds of the jet stream. A national disaster for the United States, but a glancing blow for its northern neighbor. That answer, according to the government's own advanced models, is wrong. This is the part the headlines do not capture. In August of 2014, a team of scientists at the United States Geological Survey published a groundbreaking study using a new computational model called ASH-3D. The team, led by hydrologist and volcanologist Larry G. Mastin, along with Jacob B. Lowenstern and Alexa R. Van Eaton, simulated a full-scale VEI-8 supereruption at Yellowstone. They wanted to map the continent-wide fallout with a level of detail never before possible, and their findings dismantled a key assumption about atmospheric physics. A Yellowstone supereruption does not just ride the wind, it makes its own. In Mastin's own words, the eruption essentially creates its own winds that can overcome the prevailing westerlies. Imagine the physics. An explosion ejects 1,000 cubic kilometers of superheated ash and rock into the sky, punching a column through the atmosphere to a height of 25 to 30 miles. Once it reaches that altitude, it loses its upward momentum and begins to spread out under gravity, forming a colossal, mushroom-shaped structure known as an umbrella cloud. This cloud, dozens or even hundreds of miles wide, is far denser than the surrounding air. As it expands radially outwards, it can push with enough force to overpower the jet stream. While the highest, lightest ash will still drift east, the model showed that this massive, expanding umbrella would drive a thick, dense wave of ash north, straight into the breadbasket of Canada. Calgary, Regina, Winnipeg. All lie directly in the path predicted by the ASH 3D model. The sky would not just darken. It would be blotted out by a blizzard of microscopic glass, a toxic and abrasive blanket settling over thousands of square miles of farmland, cities, and infrastructure. The science is complex, built on fluid dynamics and thermal modeling, but the conclusion is simple. The protective barrier of westerly winds that Canada has always relied on would be, in the face of a true supereruption, functionally irrelevant. The sheer scale of the explosion creates its own weather system, and that system pushes north. We cover a lot of advanced science on this channel. If you appreciate this level of detail, subscribing is one way to make sure you don't miss the next story. Now, here's the part nobody is putting on the news. The ASH 3D model is not a work of science fiction. It is a simulation of something that has already happened. The evidence is not in a computer. It is in the ground, buried beneath the prairie grasses of Saskatchewan. Geologists have identified a specific layer of ancient volcanic ash spread across the region, a material known as the Wascana Creek ash. For years, its origin was debated, but through chemical fingerprinting, scientists have proven that this ash is part of the much larger Parallel O ash bed. And the Parallel O ash bed is the geological name for the fallout from Yellowstone's last supereruption, 640,000 years ago. When the Lava Creek Tuff explosion created the modern Yellowstone caldera, it blasted 240 cubic miles of rock and ash into the atmosphere. A significant portion of it traveled north and settled over what is now southern Canada, forming a layer of physical proof that can still be dug up today near its namesake, Wascana Creek. History shows the ASH 3D model isn't a prediction. It's a retroactively confirmed fact. Yellowstone's history is written in these layers of tuff, or hardened ash. The trail of eruptions tells a story of terrifying scale and consistency. The entire volcanic complex is the result of the North American tectonic plate slowly sliding southwest over a stationary plume of hot mantle. Before the Lava Creek eruption, there was the Mesa Falls Tuff eruption, around 1.3 million years ago. It was smaller, but still a supereruption, creating the Island Park caldera. And before that, around 2.1 million years ago, was the monster, the Huckleberry Ridge Tuff eruption. It was 2.5 times larger than the Lava Creek event, ejecting nearly 2,500 cubic kilometers of material and creating the vast Henry's Fork caldera. The system has produced continent-altering explosions on a recurring cycle. The short-term breathing measured by Michael Poland and his team is just the latest murmur from a system with a long and violent memory. That kind of history is hard to ignore. If you know someone who thinks Yellowstone is just an American problem, this might be a good video to send their way. To truly grasp what is happening, you have to look past the surface. The monitoring of Yellowstone is one of the most sophisticated geological surveillance operations on the planet. When scientists like Charles W. Wicks Jr., a USGS geophysicist, talk about ground deformation, they are using a technique called interferometric synthetic aperture radar, or INSAR. It's a remarkable technology. Satellites orbiting hundreds of miles above the Earth bounce radar signals off the ground. By comparing images taken at different times, sometimes years apart, they can detect changes in the land surface with millimeter accuracy. It allows them to create a map of the entire 3,500 square mile park, showing exactly where the ground is swelling or sinking. The data from INSAR is what turns the abstract idea of a bulge into a concrete measurable map of the Norris Uplift Anomaly, showing its 19-mile diameter with precision. This satellite data is complemented by dozens of CGPS stations on the ground. These aren't like the GPS in your phone. They are deeply anchored monuments, capable of detecting minute shifts in their position, 24 hours a day. This network, largely pioneered by University of Utah professor emeritus Robert B. Smith over decades of research, provides the real-time, second-by-second confirmation of the satellite data. When the ground at Norris rose by 1.5 centimeters in late 2024, it wasn't an estimate. It was a measurement, cross-referenced between instruments in space and instruments bolted to the bedrock. This is the system that allows the Yellowstone Volcano Observatory, a partnership between the USGS, the University of Utah, and the University of Wyoming, to keep the volcano alert level at normal and the aviation color code at green with competence. They see the breath, they see the tiny shifts. They also see what isn't there, the signs of an impending eruption. Key among those missing signs is a dramatic change in the magma chamber itself. Sensationalism paints a picture of a giant cavern of molten rock sloshing beneath the park. The reality, revealed by seismic tomography, is far more complex and far less liquid. Yellowstone's upper magma chamber, which begins about 5 to 9 miles down, is not a lake of fire. It is better described as a crystalline mush, a mostly solid sponge of hot rock with only about a 9% fraction of actual liquid melt within its structure. For a supereruption to occur, a massive new injection of much hotter magma from the deeper mantle plume, located 25 to 30 miles down, would be needed to remelt a huge portion of that mush, creating enough mobile eruptible magma. The seismic and deformation signals for such an event would be unmistakable and orders of magnitude larger than the gentle swelling seen at Norris. It would involve ground uplift measured in meters, not centimeters, and intense, shallow earthquake swarms that would be impossible to miss. So, the return of the Norris Uplift Anomaly isn't a pre-eruption warning. It is a symptom of the active, dynamic plumbing system. But the threat that it brings back into focus, the threat of ash, is worth understanding in detail. The word ash is misleading. It's not like the soft carbon-based byproduct of a fire. Volcanic ash is pulverized rock and glass. Under a microscope, each particle is a shard of sharp, abrasive silica. When the ASH 3D model predicts a layer of this material descending on Canadian cities, it's forecasting a multifaceted crisis. First, there is the simple weight. A few inches of ash, especially when wet, can become heavy enough to collapse standard residential roofs. Power grids would be one of the first casualties. The fine, abrasive dust gets into transformers and switching stations, causing them to short out. When dry, it's a powerful electrical insulator. When wet, it becomes conductive, creating pathways for electricity to arc, leading to cascading blackouts. Then there is the impact on all machinery. Jet engines would be grounded instantly. Sucking in silicic ash at high altitude causes it to melt and resolidify on turbine blades, choking the engine of air and causing total failure. But the same effect happens on the ground. Car engines, industrial equipment, hospital ventilation systems. All would be clogged and destroyed by the abrasive particles. Water supplies would be contaminated as ash clogs filtration plants and turns open reservoirs into gray sludge. But perhaps the most devastating impact for Canada would be on its agriculture. The prairies of Alberta, Saskatchewan, and Manitoba are one of the world's great breadbaskets. A blanket of acidic, glassy ash would ruin topsoil, smother crops, and poison grazing land for livestock. It wouldn't just be a dark sky, it would be the shutdown of a nation's food production for a season or more. The scenario modeled by Larry G. Mastin's team isn't just an inconvenience. It's a nation-altering catastrophe, independent of the direct blast zone. Natural Resources Canada, the country's own geological survey, maintains its own volcanic risk assessments. And while the probability remains incredibly low, the physics of northern-bound ash dispersal from Yellowstone is a known factor in their long-term hazard planning. It is crucial to hold two ideas in mind at once. First, the probability of a Yellowstone supereruption is astronomically low. The USGS officially states the annual odds are about 1 in 730,000. As Michael Pollan frequently reminds the public, volcanoes do not run on schedules, and the idea that Yellowstone is overdue is a statistical fallacy. The system is not a ticking clock. It is a complex geothermal engine that spends the overwhelming majority of its time in a stable, non-eruptive state. The current activity is, by all scientific measures, normal background behavior for one of the most active volcanic systems on Earth. More likely threats are hydrothermal explosions, which happen every few hundred years and can create craters hundreds of feet across. But these are localized park hazards, not continental threats. But the second idea, equally true, is that if that 1 in 730,000 chance were to occur, the consequences would defy modern comprehension. The comfort of the jet stream being a protective shield for Canada is an illusion, broken by the simple, brutal physics of a gravity-driven umbrella cloud. The proof is not a theory, but a fact, written into the geology of the Canadian plains with ash from the last great eruption. The small half-inch bulge at Norris, now quiet, serves as the most gentle of reminders of the immense power being contained miles below. It is a change in the Earth's skin that proves the heart of the system is still beating. The monitoring is constant, the data is public, and the alert level remains at normal. The scientists at the YVO are not worried about tomorrow or next year. But the data from their own models and the evidence from the ancient rock tell a story about a potential future that cannot be ignored. The ground has stopped rising, for now. The immediate event is over, leaving behind only a slight warp in the land and a new set of data for seismologists to analyze. So, 3 questions hang over the Yellowstone Plateau tonight. Why did the Norris Uplift Anomaly stop as suddenly and mysteriously as it began? What do these increasingly well-documented cycles of breathing and flexing, this flexing faster, this breathing more erratic, truly signify for the deep complex plumbing of the North American continent? And with the geological evidence of past Canadian impact now undeniable, what is the real plan for a threat that a computer model proved was more dangerous and less predictable than we ever wanted to believe? Somewhere beneath the geysers and pine forests of Wyoming, a pocket of superheated fluid and magmatic gas, miles deep, slowly cools. The pressure it exerted for 6 months on the rock above is now stable. A pause in a geologic conversation that has been happening for more than 2 million years. The instruments are listening, waiting for the next word. The bulge, an almost imperceptible rise across 19 miles of wilderness, remains a quiet, permanent testament to the forces that shaped a continent and a sobering reminder of the 1,000 cubic kilometers of rock that made it to Canada the last time the breathing stopped. If you've stuck around this long, you are clearly as fascinated by this as we are. Maybe think about subscribing so you're here for the next story.